This video is about the uplink of multi-user MIMO or massive MIMO systems, where multiple users are sending data and pilots to a base station. And we start with how the pilot signals are utilized in order to estimate the channels, and then how the base station are using those estimates to decode uplink data. We are computing a lower bound on a channel capacity for linear receivers, and we are developing the expressions for the case when we are using MMSE channel estimates, and we are finding the optimal linear receiver based on those expressions. So recall first this uplink massive MIMO system model that I've been talking about in the previous lecture. So the received signal, y, is a vector of length m, and we have m receive antennas at the base station. And then we have the transmit power, rho uplink, with the square root of it. We have the channel matrix G, where each column is describing the channel from one user to all of the antennas at the base station. So all of those are like SIMO channels that are happening at the same time. Then we have the vector X, which is a k-length vector containing the signals transmitted from user 1 to user k. And these signals can represent both information that we would like to convey and also known sequences, pilots that are used for channel estimation, and that is what we will consider in this lecture. And finally, we're adding the noise, W1 to Wm. And the parameters are normalized here, so the maximum power is going to be rho uplink, and then x1 to xk have a power that is smaller or equal to 1. And that means that each element here has an absolute value square that on average is equal to 1 or smaller than that. And the channel to user k is modeled by IID Rayleigh fading, so each of the elements are independently Gaussian distributed and they have the same variance beta k. So this is the so-called large-scale fading coefficient. But this subscript k here is saying that every user can have a different beta value here, because users are different distances, for example, from the base station. And finally, we have the normalized noise term W, which is also complex Gaussian distributed. So what we will do now is to estimate the channel, and the way of doing that is to consider not one vector X that is transmitted here, but multiple of them, each one transmitted one after the other. So what we would like these two users here, user 1 and user 2, to do is to send a sequence of known information. That is called a pilot sequence or pilot signal. And that one will be used for the receiving base station in order to estimate the channel over which this pilot signal was transmitted. These sequences have length tau p, so these are tau p length vectors, and they have length 1, and they're also selected in order to be orthogonal to each other, which enables the base station to separate the channel estimation for the two different uses, and we will see later how to do that. And this multiplication with square root of tau p makes sure that if we take an element in this vector, we take the absolute value square of it, then on the average we get 1. So we're using the maximum power that we're allowed to use. What we will be sending over our system is a pilot matrix, square root of tau p, and then psi as a matrix form, which is containing these different pilot sequences as the columns. So this matrix here is going to be tau p as a number of rows and k as a number of columns. And by construction, psi is a unitary matrix, so we take psi multiply with itself with the Hermitian transpose, we're going to get an identity matrix, and that is something that is important to use later on. And we are sending each row of this matrix here over the channel at one particular use of it. And then we can write the received signal over tau p channel uses. Remember that the received signal is a vector of length m, and now we are stacking them tau p of them after each other as different columns to create yp, the received signal over the pilot transmission. And then we have the square root of rho uplink, we have the channel matrix G, and then we take this matrix and we are taking the transpose of it to deconjugate in order to make sure that each of the rows here are transmitted one at a time. And then we get the square root of tau p here in front. So this means that every user is sending their individual pilot sequence. And then we get the matrix here with noise. And before we were modeling one column of it, having complex Gaussian distribution with the variance 1, and now all of the elements have the same distribution. When the base station has received yp, how can it use it to estimate the channel G? Well, the first step is to do a despreading operation, which means that it is multiplying with the pilot sequences that the different users were sending in order to separate out what each of these users were actually sending. So we take yp, we multiply it with psi to form yp prime. And then we should just take this psi matrix and we should multiply it from the right to both of these terms here. So we get the first term multiplied with psi, and then we get the noise term also multiplied by psi. And now we are utilizing that these pilot sequences that the users are sending are length 1 vectors that are orthogonal to each other. So psi is a unitary matrix. So when we get psi Hermitian transpose multiplied with psi, this is just an identity matrix. So this part is going away. And then we have the noise matrix yp, which is multiplied with the same unitary matrix psi, which is sort of rotating in which basis we are looking at this random noise matrix. But because it contains IID complex Gaussian distributed elements, we will still get that type of distribution again, even if the individual elements are different. They are getting the same distribution. So we should remember that the received signal yp prime after the despreading contains a constant, square root of tau p times rho uplink, the matrix G, which is containing all of the channel coefficients, and that is the one we would like to observe, and then we have different IID Gaussian distributed elements. So we see each of the elements in G multiply with a constant plus an independent complex Gaussian distributed noise term. And from that we would like to estimate each of the elements in G in the best possible way. So how do we do that? Here's a little bit of estimation theory. Estimating Gaussian variables in noise, in particular Gaussian noise. So let us consider a simplified setup. We observe something that we call y. It's not the same y as before, and we would like to learn G, which is a complex Gaussian distributed variable with variance beta, and it's multiplied when we are receiving it with a constant p with the square root on, and then we are also being disturbed by a noise term w, which is complex Gaussian and have variance 1, and it's independent of G. And from this we would like to learn what G is and form what we call an estimate. That's what we'll call G hat. And there are many possible ways of estimating G. And one way of measuring what is a good estimate or not is to use what is called the mean squared error, which is to take the estimate G hat, subtract the true value, compute the absolute value square, and then take the average or the mean. So here we have the square error and here we have the mean. And then in estimation theory, when we are observing an unknown variable G which is Gaussian distributed and we observe it in Gaussian noise, the so-called minimum mean squared error or MMSE estimator takes this following form. So that is the estimator that is minimizing this mean squared error among all possible choices. In this case, G hat is equal to the conditional mean here of G given the observation Y. And it takes this form. We take y and we scale it in a particular way. We are taking here the square root of p, multiply with beta, and we divide by 1 plus p times beta. And 1 plus p times beta, that is actually the variance of y from the beginning. So this is the minimum mean squared error estimator that we can utilize to learn G from y. From this expression, we can see that G hat is also going to be complex Gaussian distributed, because y is complex Gaussian distributed. It is a combination of these two Gaussian variables, and then we multiply with the constant. So the estimate, G hat, is going to be complex Gaussian. It has 0 mean, and then the variance it's going to get is the square of this term here, which is p times beta square, and then we would get the square of this term, but then y have this as its variance as well, so that's why we only get 1 plus p times beta. So this is the variance of the channel estimate. So if you would like to generate channel estimates, instead of first generating y and then compute G hat like this, we can just draw random realization of this complex Gaussian distribution. The estimation error, which we define as G tilde being G hat minus the true value of G, is also going to be complex Gaussian distributed. And in this case, the original variance of G was beta, and then we subtract the variance that the estimate has, and the rest of it is the estimation error. And these two terms are not only complex Gaussian individually, but they are jointly complex Gaussian and they are independent random variables. And that we can also see here that if we add up to two variances, these terms are cancelling out and then we get beta back. So that is giving us G. So this is a general way of estimating a Gaussian distributed variable that is observed in Gaussian noise. And we had something like this in our channel estimation problem, namely the following. If we look at the element mk, so mth row, kth column in yp prime, what we will get is a constant, and then we have one complex Gaussian distributed channel coefficient between antenna m at the base station and user k. And then we have one variable of our complex Gaussian distributed noise, which is independent of all of the other elements. Then we can apply the theory from the previous slide, because this is our P that we had before, this is the G that it will like to estimate, and this is our noise term. So the MMSE estimate of GKM from user K to antenna M is the following. The estimate that we write with the hat here, G hat KM, is the expected value of GKM given that we observe this matrix, and it's actually only this element in the matrix that is of interest to us. And then we should take that element, we should multiply with this constant, square root of tau p rho uplink, and then we should take the variance, which is beta k, we should divide by 1 plus the square of this tau p rho uplink, and then multiply with beta k again. And this channel estimate is going to be complex Gaussian distributed, have zero mean, and a variance that we compute in the same way as we did on the previous slide. And it's such an important variance that we are giving it a name here, gamma k. So we should remember, gamma k, it has this particular form, and it's computed in the same way as on the previous slide. And then the estimation error, g tilde km, is g hat minus g, so the estimate minus the true value, and it's going to have the original variance of g beta k minus this gamma k term. So from now on we need to remember beta k is the variance of the true channel, gamma k is the variance of the channel estimate, and that will turn out to be the important part. This is the part of the channel that we can actually utilize to transfer data. So how good is the channel estimate? Well, the mean squared error is what we're using in order to compute something like that. And then we have the channel estimate minus the true value, the absolute value square. And this is the same thing as taking the absolute value square of the channel estimation error. And then we take the expected value of that, which gives us the variance, which was beta k minus gamma k. And beta k, we write it as this, and this was the expression for gamma k. And let's look at what happens in some different cases. If we are letting the power rho uplink be very large, so we have much stronger transmission than we have noise, then what happens in this expression here is that this term becomes large, this term becomes large, the one term here from the noise can be neglected, and then if we compute this ratio here, what's going to be remaining is one of these beta terms, beta k. So then we get beta k minus beta k, 0. So the mean squared error goes to 0 when we have a lot of power. So we get the perfect estimate. There is no estimation error left. And even if we keep the power fixed, but let the length of the pilot sequence tau p go to infinity instead, then tau p at these two places are going to be large. The one term here can be neglected, and once again we compute the ratio is beta k minus beta k is 0. So increasing the power or increasing the length of the pilot sequence, that is sort of the same thing. They are showing up here together because this is the total energy that we're sending in our pilot transmission. And it doesn't matter if it's on every symbol that we're transmitting or if it's because we have a long sequence. Here is a simulation of this. So say that beta k is equal to 1. And the signal to noise ratio is then just equal to rho uplink. And that's what we're showing here on the horizontal axis, the SNR in dB scale. And here we are showing the mean squared error. The solid black line here is when tau p is equal to 1. And if we are increasing tau p to 10, then we are effectively moving the curve 10 decibels to the left, because we get effectively 10 times more power because we are using this whole sequence. And we see that as we increase in the SNR, then these curves are going down. So we get the smaller and smaller mean squared error. And we can think about what is a typical mean squared error that we would like to achieve. Well, maybe 10 to the power minus 1. In that case, we have 10% error. That could be at least enough in some cases. And in this case, we would like to have either 0 dB when we have a pilot sequence of length 10, or we need 10 dB if we have a pilot sequence of length 1. And 10% error might seem large, but actually in massive MIMO cases when we have a large number of elements, it might seem like, okay, we have 10% error in each of them and that is summing up to something large, but actually it's the opposite effect, because we can have small errors on all of different terms, and then these ones will sort of average out, just as those asymptotic motivation we saw that the noise was averaging out, for example. We will now move on to the data transmission, and I will talk about a capacity lower bound. So previously we have been looking at the cases when the receiver knows the channel perfectly, and then we can compute the exact capacity in different point-to-point MIMO cases. But in practice, the receiver can't know the channel perfectly. So say that we have a desired signal X that is transmitted. It is scaled by a power term rho. So we have the square root of rho here. Then it goes over a channel, G. We add noise to it, W, which is uncorrelated with the random channel G. Then what we receive is Y, which is equal to square root of rho times G times X plus W. And this signal goes into a receiver that would like to produce an estimate X hat. So an estimate of the transmitted desired signal X. And when it's forming this estimate, what does it have to access? Well, it has this received signal Y, and it has some kind of channel information that we call omega. And this channel information is something around the channel coefficient G. And what we have considered earlier is that we are knowing the exact realization of G, even if it's a random number. But now we will generalize that, because in practice we can't know the exact value. We have these estimation errors that I just talked about. And then we can't compute the capacity exactly, but we can compute the capacity lower bound. And here is one typical result that you can find in the book Fundamentals of Massive MIMO. So it contains a log 2 of 1 plus a signal to interference and noise ratio term. So what it contains here is the power rho. Then we have an absolute value square of the channel, but it's not the actual channel G, but it is our estimate of G given the channel information that we have, omega. Then we divide by rho times the variance of G given omega. So this is our uncertainty around this estimate of G given omega. And then we have the variance of the noise given what we know about the channel. And in some cases, omega can contain later on not only information about our desired channel, but also channels to other users. And W will then contain interference from those users. And that is where this omega and W are entering to this expression as well. Since we are considering a fast fading channel where the realization of the channels are changing all the time, then this is going to be a random number, and the expectation here is once again taking the expectation over the different channel realizations. So the capacity is smaller or equal to this term, and usually we should expect it to be smaller. So equality here would only appear when we have perfect knowledge of the channels. The rest of this lecture will be about computing these expectations and variances in this lower bound, and then maximize the lower bound with respect to how the receiver is operating. Let's now look at this uplink system model again, and now we will particularize it for data transmission, because that is what we will consider next. So we still have the received signal vector Y, we have the channel vectors G, we have X, which we are transmitting, we have the noise, and we have rho uplink. And it is the vector X that we will now look more deeply at. So each signal xk transmitted by user k will be divided up into two terms. qk is the data symbol. It's going to be complex Gaussian and have variance 1. And then eta k is going to be a power control coefficient. So it will be used later on in the course in order to figure out if the user should be transmitting with its full power, which represents by 1 here, or if we should cut it down towards 0 when it transmits with no power at all. And we will keep eta k as a constant for several lectures now, but then towards the end of this course we will optimize this parameter. And remember that the power constraint that we are considering is that the absolute value square of x have an expected value that is smaller or equal to 1, and we get a 1 from q here, and we get smaller or equal than 1 for eta k, like this. And we have the same type of models for the channels as before. We have the same distribution of the noise as before. I will now rewrite this model without using x, but instead use q and eta. So here's the way to do that. We are gathering the q terms, q1 to qk, in a vector q, which is of length k. And then we multiply it with another matrix. In this d eta matrix, we have eta1 to eta k. And then we wanted to have the square root of those ones, so we write the matrix square root like this, which just means that each diagonal element here has a square root on it. So we multiply these two together, and that is giving us the same thing as x as before. Okay, what the receiver would like to do is to use y here to guess what each of the transmitted signals q1 to qk is equal to. So let's zoom in on one particular user, user I. We would like to select a receiver filter, AI, such that if we take the inner product, AI with y, we are getting something in the end that is approximately equal to qi. And approximately, yeah, we will see later what it means, what is a good sense of saying that they are approximately the same. But remember that this is essentially the same thing we did when we had the Seimer channel before. Then we had this maximum ratio combining vector that we took an inner product with to produce an estimate of the signal of interest. Now, when we are computing this inner product, we get multiple terms. So we take AI Hermitian and we multiply it with y from the left-hand side. So then we get this term here multiplied with AI, and then we get the noise term multiplied with AI. If we expand this expression here, we can take each column of G, which is a channel from one user. Say we have GK here. Then we take one term from this matrix. We have the square root of eta k. Then we have the square root of row uplink here. And we have one element from the Q vector, namely QK. And then we have a summation over all of different users or all of the columns in G. If we look at the summation here, when k is equal to I, we have a term multiplied with qi, and that term we would like it to be similar to 1 so that we get approximately qi. And then we have the summation over all of the other interfering signals sent by other users, and we would like their terms here in front of their qk to be close to 0, and we would like the noise term also to be close to 0. And one of the problems that we would like to solve is how to select AI in a good way. And we would like to figure out what does a good way mean. Note here that we are applying this receiver filter for one user only. There is no concept of successive interference cancellation. One could in principle add that on top of what we're describing here, but we will refrain from doing that to not make it overly complicated. So we are taking Y, we select one receiver filter for a particular user, and then we only care about making sure that this inner product becomes very similar to that user's signal. And in order to figure out a good way of selecting AI, we should have the end performance in mind, namely this capacity lower bound. We would like to select AI to maximize it. And in order to do that, we first need to compute all of these terms here in the numerator and the denominator. So there are 3 different terms. So that is what we will do next. And remember, in our case, these G, omega, and rho have different meanings. Rho, when we are considering a particular user I, is rho uplink times eta I. G is GI with an inner product with the receive filter AI. X, which is the signal we're sending that's actually not showing up clearly here, was equal to QI. Omega, which is the information that the receiver has, is the estimates, the MMSE estimates that we computed earlier for all different users. So these are vectors containing the estimates of each of the particular user's channel elements. And W prime here, I'm using the prime now because we would like to separate it from the W vector that we have for the noise. It contains both this noise term, where we have the noise vector and in the product with the receiver filter, and all of the other added terms that we had before. K goes from 1 to capital K, we exclude K equal to I. And then we have these terms here, we have the interfering signal, we have the power of them, and we have the inner product between the channel and the receiver filter. So given these parameter values, we will now like to compute all of these three terms. So this is the expression. Let's focus first on this expectation in the numerator. Here's the computation of that one. So expected value of G given omega. And G was equal to this inner product. So we write it here. Omega was the channel estimates. And when we are knowing the channel estimates, one thing that is going to be constant is our receiver filter. Why? Because AI will somehow be selected at the receiver given the information that the receiver has. So it must be a function of these estimates or just some stupid other choice, but it's not based on any randomness that the receiver doesn't know about. So for that reason, we can take AI and we can move it in front of the expectation. Then we take that GI can be separated into GI hat, which is the estimate that we know, minus the estimation error, G tilde I. So we take the expected value with respect to GI and we separate it based on these two terms. So we have the expected value of GI hat given the channel estimates and minus the expected value of the estimation error given the estimates as well. And now we note that if we know the estimates, well then the estimate here is a constant. So we can just remove that and write AI Hermitian GI hat. And then the estimation error is independent of the estimates. So if we know the estimates, that doesn't tell us anything about the estimation errors. So we can just drop that information and write the expected value of the estimation error, and that one have zero mean. So this term goes away. So now we have computed a term in the numerator. It's the inner product between the channel estimate of the user of interest and its receiver filter. That's what should go inside this absolute value square. It remains to compute the two other terms, so let's continue with the next term, the first term in the denominator, the variance of G given omega. So we have this term here, and the variance can always be expanded as the expected value of the absolute value square of the term minus the expected value of the term with an absolute value square outside. So this is something that we can always do when we deal with variances. And since we have a conditional variance, we know omega, we put these conditions here as well. And we already have computed this term here. That was what was showing up in the numerator. So what remains is to compute this term. So here is the computation of that one. G was still in the product between AI and GI, and omega is the information that we know. We can expand this term here as AI Hermitian GI and then GI Hermitian AI because we have the absolute value square. And AI is a constant when we know omega, so we move it outside expectation. And then we take the GI Hermitian GI and we are utilizing once again that G is equal to the estimate minus the estimation error. So if we put that into the expression and expand everything, we get four terms. We get the outer product of the channel estimates, the outer product of the channel estimation errors, and then we get the cross terms when we have one estimate and one estimation error. And then we have the expected value of all of this given the channel estimates that we know. And if we know the channel estimates, then the first term here is a constant because it only contains the channel estimates. Then the estimation errors are independent of the channel estimates, so knowing those ones doesn't provide you with any additional information. And therefore we are just putting in its covariance matrix here, which is an identity matrix, and then we have beta I minus gamma I. So this was the variance of the estimation error terms. Then we have these two cross terms when we are knowing the estimates, but we don't know the estimation errors. So when we compute the expected value, we get the expected value of the errors, and those have a mean value that is 0. So we just get 0 for those two terms. So this is the computation, and if we are summarizing it, we get in parentheses here the outer product of the estimates, and then we have the covariance matrix of the estimation error, and then we have AI multiplied from both the right and the left hand side. So we're using the same properties as before and compute this term. What remains now is to compute the second term in the denominator, which was the variance of the so-called effective noise that contains both the actual noise and interference from the other users. So it's this term here where we have interference from the kth user, where k goes from 1 to capital K but is not included in the user of interest number I. And then we have the noise term, and we should compute this conditional variance given the information that we have, omega, which was the channel estimates. And whenever we compute the variance, we can expand it in these two terms, the expected value of the absolute value square minus the square of the mean value. And this mean value here, if this is W prime here, this mean value is going to be 0 because the randomness is in QK and in W, and both of them have 0 mean. So computing this variance is the same thing as only computing the expected value of the absolute value square of W prime. And when we are computing something like this, we have multiple terms here, and computing the expectation of it would be to compute the expectation of each term in absolute value square, and computing the expected value of cross terms when we take, for example, one of the user term and the noise term, or these user terms for two different users, and multiply them together, one with the conjugate. And all of those cross terms are going to be 0 because we have 0 mean on all of these types of randomnesses. So we can write now this term as being a summation over all of the users, and then the absolute value square of the randomness that we have for each of the users. And the randomness comes into the channels here and the data signals. And then here we have the absolute value square of the randomness coming from the noise with the expected value. And computing its term here, each of the data signals is independent of the channels, and they have a variance equal to 1. So this term is just 1. Computing this term here, where we have the inner product between A and G, and then absolute value square and expectation, that is the same type of thing that we did in the first term in the denominator. The only difference is that now the indices here are different. But that doesn't change our computations. We will still get these parentheses here where we have an outer product of the channel estimate, now with index k. And then we have the variance of the estimation errors in identity matrix. And then we have AI Hermitian and AI on the other sides here. And here we have the constant, and we have the 1 from the data signals here. Finally, when we are computing this term over here, the noise vector is independent of AI and has an identity matrix as covariance matrix. We put it here, and we are multiplying with AI from both the sides. So this is the second term in the denominator. If we put all of these things together, all these complicated computations, we are getting this type of structure. So we have an expected value of log 2 of 1 plus rho uplink and eta I. Then we have the inner product between AI, the receiver filter for user I, and the channel estimate of that user, and absolute value square. And in the denominator, we have that we can put all of the terms in the matrix, BI, that contains the summation over all of the other users, channel estimates with outer product, and the power that each of them are transmitting with. And here we have the estimation error for all of the users, including user I. And here we have the covariance matrix coming from the noise. And then in all of these terms, we should multiply with AI Hermitian from left hand side and AI from the right hand side. So that's why we can write it here as a matrix BI that contains all the terms, and then we have AI multiplied from both sides. So this is the capacity lower bound for user I. So how do we pick AI to optimize something like this? Well, this term here have a particular structure that is known in mathematics as a Rayleigh quotient or generalized Rayleigh quotient. So there's the result here saying that when we have a ratio looking like this, we have an inner product between A and B and absolute value square divided by A Hermitian capital B times A. So B, lowercase here, and capital B are two different constants. This is the vector, this is the matrix. And for a given lowercase b vector and invertible matrix capital B, this term is maximized when A is equal to B multiplied with capital B inverse. So what is the intuition of that? Well, say that we are removing this B matrix here or changing it to an identity matrix. In that case, we get a ratio looking like this, which is going to be maximized when A and B are the same, because here we are normalizing with the norm of A, and here we are maximizing this type of inner product. And of course, by Cauchy-Schwarz inequality, we would like A and B to point in the same direction. And this is essentially what we were doing when we did maximum ratio combining. We are selecting our receiver filter to be equal to the channel. And then when we have this additional B inverse term here, it acts as some kind of whitening. So when there is no interference and no estimation errors, B is going to be an identity matrix, and in that case we get something like this, and we get maximum ratio combining out of this. But when we have this interference from other users, then we would like to whiten the interference and noise term by using this B inverse here. So that is sort of the intuition behind this type of result. And we can use this result straight away in order to maximize our capacity lower bound with respect to the receiver filter. And we already had defined this B matrix with an index, and we also had an inner product between our receiver filter and a vector, namely the channel estimates in the numerator. So we can write our capacity lower bound like this. We had the BI matrix that I already introduced, and BI vector is the channel estimate, and then we include this power scaling term as well. Then what we have inside here is exactly what was showing up in the Rayleigh quotient theorem. So we are maximizing this expression, this ratio, by selecting AI to be equal to capital BI inverse multiplied with this BI vector. And then we can just replace BI with this channel estimates, and we have this power scaling term. And this is called minimum mean squared error combining, or MMSE combining. I said earlier that we would like to select AI so that its inner product with the received signal Y is going to be very similar to the desired signal QI. And this is called MMSE combining because this is actually minimizing the mean squared difference between the inner product and QI. Geometrically, we can view this receiver filter like this. Say that we have a channel estimate for the desired user, gi hat, that points in a particular direction. It's a vector, so it will always point somewhere from the origin. Then we have the estimates of all of the other users, and they are spanning some kind of space. So if we have only two users, we can say that they are spanning a plane like this. So the two vectors are lying in that plane. And when selecting our receiver filter, we can put it as any vector in this illustration here. If we make it aligned with the channel estimate of the desired signal, we will maximize the gain of the channel, the numerator of the SINR expression. But that's not the optimal thing to do. We can also select something that is pointing orthogonally to the subspace where all of the other users' channels lie. By selecting that, we would minimize the denominator of our SINR expression, but the optimal thing is to do something in between, to put AI pointing somewhere in between these two different ones. And the way of computing it is exactly to take our channel estimate, and then we are rotating it using this BI inverse matrix, so that it's moving towards the case where we are getting zero induced interference from these estimates. In this lecture, we started with the uplink channel estimation, where we have k users sending pilot sequences to the base station, and they are of length tau p, which is greater or equal to the number of users. And we were computing the MMSE channel estimates. Then we shifted focus to the data transmission. We were computing a capacity lower bound for linear receivers. We were simplifying that expression when we are using this MMSE estimates, and then we found the optimal linear receiver that maximizes that lower bound.